Hi everybody. So in this video, I'm going to be going through lesson 6 for unit 6, which is all about the U-Substitution method for evaluating integrals. Now, in class today, we talked about and we reviewed how when we learned to take derivatives, one of our rules was the chain rule. As a quick recap right now, let's go over the chain rule again. So the chain rule was the rule that we applied whenever we had an outside function and an inside function. In this particular example, the outside function would be e, and the inside function would be the sine of x. So if you want to write this in a different way that makes it a little bit more obvious which one is the outside and which one is the inside, one of the ways you could write this, just so you have a visual of the outside and the inside, is e to the parentheses sine x. Now, when we learned to take the derivative of this earlier this year, we learned that in order to take the derivative, you start by taking the derivative of the outside, which the derivative of e to the something would just be e to the something, and you leave the inside function alone. Then you multiply by the chain, which is the derivative of the inside. Since the inside function here is sine, the derivative of that would be cosine. Now remember, when you do chain rule, you leave the inside alone. So sine of x would just stay here inside. Because the rule, and I'm going to write down this in words, is derivative of the outside and then multiply by the derivative of the inside, so times derivative of the inside. And that was our rule for doing the derivative. We talked today in class about how to undo that, which would be to start by doing the antiderivative of the outside and then dividing by the derivative of the inside instead of multiplying, because we're going backwards. Since we are learning about finding these antiderivatives, we know that this is one way to do it, is sort of undo chain rule intuitively. And another thing that we're going to talk about in today's video is what do we do when undoing the chain rule is not so obvious? So maybe it's hard for us to tell what is the outside function, what is the inside function. Maybe we just are people who prefer to have a step-by-step process for figuring out these answers. There is actually a systematic method for undoing the chain rule, which is called U-Substitution. So what I'm going to do in this video is teach you this method and then show you a few examples where we can actually kind of do the problem two ways. We can do the problem without doing U-substitution, just sort of doing the antiderivative of the outside and dividing by the derivative of the inside, versus we can actually do it with U-substitution to see how the two methods compare. And that's going to allow us to hopefully have some options going forward so that if we wanted to do a problem, we have more than one solution method. And hopefully that means we're more likely to get it right because we can always figure out something that will work. Let's go ahead and go through what the U-substitution method is. So the U-substitution method is just a formal way of figuring out the outside, figuring out the inside, and then undoing that by following a set of steps. So step number 1 in the U-substitution method is to choose a function u. Now, in the U-substitution method, you want your u to be the inside function, the part of the equation that would have caused the chain rule to happen in the first place. In this particular example, if I'm trying to find the integral from 0 to pi of sine of x times e to the cosine of x power, because cosine of x is the power here instead of just a regular x, that would have caused me to have done chain rule originally. So in this particular example, my u would be cosine of x because that is the inside function. It's inside of the e function. The second step of U-substitution is to calculate your du. Now, when I say du, I mean the derivative of whatever you just decided that u was. Basically, what you're doing here is you're identifying the chain. So in order to figure out what the chain would have been when we took the derivative, we need to figure out what the derivative of the inside function was. In this case, the derivative of u, and I would write du divided by dx because it's the derivative of u with respect to x, would just be the derivative of cosine, which would be negative sine of x. So all you're doing is you're taking the derivative of whatever you identified as your u function. You're just taking the derivative of that thing. The next thing that we're going to do, and this is the part where if you're somebody who, just prefers to have a set of steps to follow, this sort of helps you divide by the chain rule. You're going to solve for dx. So that literally means get dx by itself. Now, in order to do that, we're going to look at this equation right here. And in order to get dx by itself, we're going to start by multiplying by dx on both sides. And that's going to give me du equals negative sine of x times dx. And then we're going to divide by negative sine. So we're going to have dx equals du divided by negative sine of x. So you're just getting the dx by itself. The next step it says here is to substitute. And I know that that's listed in the same step as the getting the dx by itself, but it's actually a very important step, kind of almost like a separate step of the problem. The two pieces that you need for your substitution are this piece right here, whatever u was, and this piece right here, whatever dx was. So we're going to go ahead and we're going to substitute. Now, I want you to think about all this stuff that I just did as sort of work that you're doing on the side. You're sort of doing that in preparation for doing the problem. You're not actually doing the problem yet. You're just helping your brain sort out what was the inside function, what was the chain, and then we're going to start substituting. So here's how we substitute. Since u is equal to cosine of x, in this equation, I'm going to replace cosine with u. And since dx is equal to du divided by negative sine, in this equation, I'm just going to replace dx with du divided by negative sine. So here's what that's going to look like. We're going to have the integral still, and I'm not going to fill in the bounds yet. I'll explain why in a second. I'm going to just copy down the sine of x part of this problem, and I'm going to copy down the e to the something. But in the exponent here, I'm going to change it to a u. I'm substituting. I'm replacing the cosine with a u. And instead of the dx, I'm going to write du divided by negative sine of x. Now, let's talk about the bounds. So before we do anything else, let's talk about figuring out the new bounds of this problem. Because if you look at the new problem that we've got here, we're sort of replacing a lot of the x's with u's. We need to replace the original bounds, these numbers right here, the pi and the 0, with new numbers that are going to be u numbers instead of x numbers. So to figure out those numbers, I'm just going to take the pi and the 0 and plug them into my u equation. Since u is equal to cosine of x, if I plug in pi, the cosine of pi is negative 1. And since u is equal to cosine of x, when I plug in 0, cosine of 0 is actually positive 1. So my new bounds would be negative 1 on the top and positive 1 on the bottom. Now here's why this method works. Once you do all this work, once you find your u, you find your du, you solve for your dx, and you substitute and change your bounds, here's the cool part that happens. This is sort of the payoff. When we look at this new integral that we have here, you'll see that there's a sine of x here, and we're dividing by a sine of x here. Because we're multiplying and dividing by the same thing, those two parts of the problem essentially cancel out. They undo each other. We multiplied and we divided by the same thing. So the new simplified integral that I need to do is the integral between 1, which is the new bottom number that I calculated, and -1, which is the top number that I calculated. And there is still this negative here. So instead of writing e to the u du divided by -1, I'm just going to know that that's negative e to the u du. This problem that we're looking at right here is a much simpler problem than the one that we originally started with, because I can find the antiderivative of e to the something really easily in my head. The antiderivative of negative e to the something would just be negative e to the something plus c, and then I need to evaluate that between 1 and -1. If I go ahead and do that, I get negative e to the -1. I know that my plus c's are going to cancel. I've done this enough times now, so I'm going to have negative e to the -1 minus, and I'm going to have negative e to the +1. And two minuses make a plus, so I just have negative e to the -1 plus e, and that's my final answer. Now, I know that this seems like a really long process, and the first few times you do it, it actually seems a little confusing for some students, but it is really nice because if you learn this process, if you're somebody who doesn't see the outside function and the inside function and the chain very well without, having a step-by-step process to follow, this does give you a step-by-step process to follow. Let's go ahead and try the next problem in two different ways. So this guy right here, number 1, we're actually going to do in two different ways. The first way I'm going to do it is the way that we talked about in class, which is just sort of identifying the inside function and then dividing by the chain. In this case, the inside function would be this 2x squared plus 1. And the reason that that's the inside function is because we have a power on the outside of that, the something squared. One thing that often helps students for a problem like this in order to figure out the antiderivative is to actually start by rewriting this with a negative exponent. I know a lot of students actually prefer that. So they rewrite the problem like this. The integral from -1 to 2 of 4x parentheses 2x squared plus 1 to the -2 power. For me personally, I believe that that also makes it easier for me to identify the outside function, the inside function, and then do the antiderivative later on. Again, the inside function that I identified here is the 2x squared plus 1. Now, the chain of that inside function would be 4x. So what we learned in class today was we could just divide by the 4x, which makes this part of the problem cancel out, and then just do the antiderivative of the outside function. In this problem, the outside function is the -2 power. So when I undo something to the -2 power, I'm going to add 1 to the power, so I have -1, and then I'm going to divide by my new power. Now remember, the 4x is canceled, so if I divide by -1, I just have -1. And the inside function stays the same. Just like when we took the chain rule, we do the derivative of the outside, leave the inside alone. When we undo the chain rule, we do the antiderivative of the outside, leave the inside alone, plus c. And we're going to evaluate that between -1 and 2. If I go ahead and plug in those numbers, I have -1 times 2 squared. If I plug in the number 2 is 4, times 2 is 8, plus 1 is 9 to the -1 power. That's kind of plugging in the first number, the top number, which is 2, minus, if I plug in my bottom number, I have -1 times -1 squared is 1 times 2, which is 2, plus 1 is 3, to the -1 power plus c. Now, again, I've done this enough times to know that the c's are going to cancel, and a -1 power really means to move that to the bottom. So this is -1/9. These two negatives make a positive, so I have plus 1/3. Now, 1/3 is really 3/9. That's sort of something I'm going to do in my head in order to make sure that I can add these together successfully, and so I get 2/9 as my final answer. Now, what if I wanted to do this using this U-Substitution method? What would that look like? Well, step number 1 of the U-Substitution method is to do exactly what we just did. Identify the inside function, and we call that U. In this case, u would be 2x squared plus 1. The second step would be to figure out what the chain would have been. So in this case, the chain would have been the derivative of the inside function, which is du over dx equals 4x. You'll notice that that's the same thing I divided by here. The last thing I need to do is get the dx by itself. Now, in order to get dx by itself, I'm just going to multiply by dx on both sides, and then at the same time, I'm going to divide by 4x. So that means that I get du divided by 4x equals dx. And this is sort of the work that I do on the side before I start my U substitution. Now, the important pieces for the U substitution part of this problem would be the u here and the dx here. So when I do my U substitution, I'm going to have the integral. And again, I'm going to fill in the bounds in a second because I need to change those numbers because I did a U substitution. I'm going to have the integral from some numbers. I'm going to copy down the 4x, and then I'm going to copy down the parentheses, but instead of having 2x squared plus 1 to the negative 2 power, I'm going to substitute that is u. I decided to call 2x squared plus 1 u now, and I'm going to change the dx to what I figured out here, which is du divided by 4x. Now I do need to change my bounds. So in order to change my bounds, I'm going to take this 2 and this negative 1, and I'm going to plug them into this top equation here. So I'm going to plug in 2, and I'm going to plug in negative 1. When I do that and I plug in 2, I get 9. And when I plug in negative 1, I get 3. Now, the nice thing is that unlike here where I just divided by the chain, this sort of divides by the chain for me. The 4x's cancel. It sort of sets it up so that I can see that it divides really easy. And then I'm going to have the integral from 3 to 9 of u to the negative 2 power du. Now, the antiderivative, again, of something to the negative 2 power would be something to the negative 1 power, and then I need to divide by that new power, so I'd have negative 1 plus c evaluated between 3 and 9. When I plug in my numbers, I have negative 1 times 9 to the negative 1 plus c minus negative 1 times 3 to the negative 1 plus c. And you'll notice that this step of the problem actually looks exactly like this step of the original way we did this problem. So the U substitution is just a different method to get to the same place. Once I get to there, I'm just going to go ahead and use the answer I already found, and I get 2/9 as my answer for that problem as well. Now, you do not have to do every problem two ways. You really just have to do it one way that works for you. And what I like to think about it is, as the U substitution method is sort of a backup method. If I can't easily see what the original function was, what was the inside, what was the chain, then I'm going to use U substitution to figure out some of those trickier questions. Let's go ahead and talk about problem number 2. So I'm again going to do, this is the last example that we will do in the video, but I'm going to do problem number 2 because I do want to show you two different ways of approaching the same question. So in problem number 2, the first way we could do this problem is sort of the method that we talked about in class today. I'm going to identify the outside function and the inside function. Now here is an example where it's a little less obvious what's the outside and what's the inside. In this case, I'm going to make tangent the inside function. Now, the reason I'm making tangent the inside function is that I happen to know that secant squared is the derivative of tangent. One way to sort of visualize this a little bit easier is that we could think about this as tangent to the first power. So that's sort of one way to think about it, is that this is tangent to the first power. So the outside function is that power of 1. The inside function is tangent. And I'm going to do that because the derivative of tangent is secant squared. The next step of what we talked about in class is that once you've identified the outside and the inside function, you just divide by the chain, which would be the derivative of the inside. The derivative of tangent is secant squared of x. So those two parts of the problem would cancel out. And if I go ahead then and take the antiderivative of the outside, if I started with something to the positive 1 power, the antiderivative would be to the positive 2 power. And then I would have to divide by 2 or multiply by 1/2 in order to cancel out that new power. And again, we leave the inside function alone. So just like when we do chain rule, we take the derivative of the outside, leave the inside alone. When we do the antiderivative of a chain rule problem, we do the antiderivative of the outside, leave the inside alone, plus c. And I'm going to evaluate that between 0 and pi over 3. Now, if I go ahead and I plug in those numbers, I'm going to have 1/2 times the tangent of pi over 3 squared plus c minus 1/2 times the tangent of 0 squared plus c. I know my plus c's are going to cancel. Again, we've done this enough times that we know that. Now, going back to what is the tangent of pi over 3, if I think about the unit circle, pi over 3 would have been this angle right here, and the ordered pair for that angle would have been 1/2 comma root 3 over 2. Now, tangent is y divided by x, so I'm going to take the y number and I'm going to divide it by the x number, which means I'm going to get the square root of 3. So I'm going to have 1/2 times the square root of 3 squared minus the tangent of 0. This would be the point 1 comma 0. And I'm going to again do the y divided by the x. So the tangent of 0 would just be 0. Now, a square root squared just gives me a 3. So I would have 3 over 2 as my final answer. There are a couple tricky parts that I foresee being issues in this problem. The first tricky part is identifying that tangent was actually the inside function. It doesn't really look like it at first. And again, the only reason I knew that is that I know the derivative of tangent is secant squared. I could see the chain right there in the example problem. The second tricky thing is being able to find those tangent values. I know that the unit circle, we might be a little bit rusty, so a good strategy is always to sketch the unit circle in the corner, label the ordered pairs, and be able to find the numbers that way. It's not important to have it memorized as long as you know how to find it if you need it. Now, option number 2 is to actually do this problem using a U-substitution. So step number 1 would be to identify the U, which is the inside function. Again, I'm going to know that that's tangent because I can see the derivative of tangent, or in other words, I can see the chain right next to it. The derivative of tangent is secant squared. Then I would take the derivative in order to identify what that chain would have been. So du over dx equals secant squared of x. And I'm going to solve for dx. I'm going to multiply by dx on both sides and divide by secant squared, which means I have du divided by secant squared of x equals dx. Now, this is sort of all work that I'm going to do on the side before I actually start my problem. So the next step is going to be the U substitution part. And the two important parts for the U substitution are the U and the dx. So my new integral is going to be, instead of tangent, I'm going to have U. And then I'm going to copy down the secant squared from the original problem. And instead of writing the dx, I'm going to write the du divided by secant squared of x. Now remember, just like in the original way we did this problem, we should realize at this point that the secant squareds cancel, just like we did over here at the very beginning of the problem. I do need to adjust my bounds. So I'm going to take the pi over 3 and I'm going to plug it into tangent of x. And I'm going to take the 0 and I'm going to plug it into tangent of x to get my new numbers. We know from what we just did that when you plug in pi over 3, you get the square root of 3. And when you plug in 0, you get 0. And now I can go ahead and simplify. So this now becomes the integral from 0 to the square root of 3 of just u times du. You can see that that's a much simpler antiderivative. This is really u to the first power, so the antiderivative would be u to the second power, and then I need to divide by that new power. I'm going to go ahead and evaluate between 0 and the square root of 3. Now when I plug in my numbers, I'm going to have 1/2 times the square root of 3 squared plus c minus 1/2 times 0 squared plus c And then the square root of 3 squared is still just 3, so I would have 3 over 2 as my final answer. Okay, thank you guys so much for watching. I will see you soon for some practice, and have a great rest of your day.